In this video, we are going to be looking at the regioselectivity of electrophilic aromatic substitution. If you look at the scheme that I have here, we're doing a nitration reaction on some substituted benzene. That substituent is just represented by an R group. And you can see we have the potential to form three different products. So first, a little bit of terminology to differentiate these products in the position where the substitution occurs. Right, so you can see the first product, that substituent, that nitro substituent, is one bond away from where the R group is on the ring, right? And so we refer to this position and this type of substitution as ortho substitution, and this position relative to the R group as the ortho position. Right? In the second product, you can see that that nitro group is added 2 positions away from where the R group is on the ring. Right? And we refer to this position as the meta position and the substitution as meta substitution relative to the R group. Right? The third product, you can see that that nitro group is across the ring, or 3 positions away from where the R group is, or 3 bonds away. And we refer to this position as the para position. Right? We can also look at these positions on the starting material and see that there are actually 2 different ortho positions here and here. Right? There are 2 different meta positions. Right? And then obviously there's just 1 para position. Okay. Another term or position name to know is the position where the R group sits on the ring, and we refer to that as the ipso position, right? And although we can't do ipso substitution, right, we can't get a substituent to sit on the ipso carbon, we do need to know that term because we're going to look at resonance structures in this video where a charge ends up on the ipso carbon. All right, so similar to the videos on reaction rate, these videos on reaction regioselectivity are going to focus largely on the Arenium intermediate. Okay, and really what we're going to be doing is assessing the stability of the Arenium intermediate to figure out which reaction pathway a substitution is going to go through. Okay, so what we'll do on this piece of paper is we're going to draw out what the Arenium intermediate looks like for each type of substitution, right? So if the nitration occurs in the ortho position, what does that Arenium ion look like? If the nitration occurs in the meta position, what does that Arenium ion look like? Same thing for the para position, all right? So I'm going to draw out for you that ortho substitution. And we're going to focus just on the formation of the Arenium intermediate, not the product, right? We know that the product, once the addition in the ortho position occurs, the elimination will occur to keep the electrophile in that position. All right, and so to do this, we're just going to use some generic arene, right? So we'll put an R group here. Okay, and the electrophile, it doesn't really matter what the electrophile is, so just for simplicity, we will use the electrophile E+. Right, and we'll show pi electrons grabbing the electrophile and then forming the Arenium ion. So substitution in the ortho position relative to the R group. Okay, and you can see the charge forms in the meta position relative to the R group. Right, now realize that this Arenium ion exists as a combination of 3 resonance structures, right? So this is one resonance structure, right? We can push these pi electrons around to form a second resonance structure. right? And then we can push them further to form our third resonance structure. Right? And so you can see that we have three different resonance structures, and these three resonance structures averaged together represent the overall Arenium ion intermediate, right? The Arenium ion doesn't look like any one of these in particular, but it's some average of those three, some weighted average of those three, right? So we can even get kind of an average picture, or draw this as an average picture. Again, where we have ortho substitution, right? You can see after we do that initial addition, there are 4 pi electrons left in the ring, and those 4 pi electrons are shared by all of the atoms that didn't undergo addition, electrophilic addition. And so we'll just represent those electrons, or where those electrons are, with a dotted line. And then we'll write a 4e minus in the middle. Okay, and then that charge is being shared between 3 different carbons on the ring. Okay, and if you look at what those carbons are, they are the 2 metacarbons and then the ipso carbon. And so we'll put a positive charge in parentheses to represent a significant partial charge, right? 1/3 positive charge. Okay, and so this structure would represent the overall or average resonance structure of the Arenium ion that occurs through ortho substitution. What I want you to do now is pause the video and draw out the same draw out what the Arenium ion would look like whenever a molecule undergoes meta substitution, and draw out the resonance structures for a molecule that would undergo para substitution. All right, and see what you get, right? And what we're going to be focusing on is where that charge is concentrated. So go ahead and pause the video, and then we'll come back and take a look at those other resonance structures. All right, so if you pause the video, all right, hopefully you were able to come up with resonance structures for the meta substitution that look like this, right? And resonance structures with the para substitution that look like this, okay? So you can see for the ortho and para substitution, that charge density, that positive charge, is concentrated on the meta and ipso carbons, right? For both of these substitution pathways. All right, in contrast, the meta substitution puts that positive charge density on the ortho and para carbons. All right, and so if you look at these 3 average resonance structures, right, that represent the 3 different substitution pathways, hopefully you'll notice that because in the ortho and para substitution pathway, there's a positive charge on the ipso carbon, those are going to be the pathways that are most affected by a substituent, right? Whether that substituent is electron donating or electron withdrawing, right? Any substitution that occurs on the carbon that has a positive charge is going to have a significant influence over the stability of those Arenium ions, all right? Our group will have some influence over the stability of this intermediate as well, but because there's no positive charge on that ipso carbon, it's not going to have as a significant effect as it will here. All right, so let's take a look at some specific examples. All right, so here are our 3 average resonance structures. Okay, and I've reorganized them, right? So I've grouped the ortho and para together just to illustrate that the positive charge is concentrated on the same carbons relative to the R group in both of those Arenium intermediates, right? And then the meta substitution has positive charge concentrated on different carbons. All right, so what is this going to look like if that R group is an electron donating group? All right, so an electron donating group. And kind of a go-to electron donating group is a methoxy group, right? So we're going to use the uranium ion generated from the ortho substitution of anisole. Right? And we're going to investigate not this structure, right? But we're really going to be looking at this structure here, this resonance structure where the positive charge sits on the ipso carbon. Okay, so even though the overall Arenium intermediate is an average of these three structures, for this lecture, we're going to use this to represent the Arenium intermediate because this is probably going to be most illustrative of how that R group affects the stability of the Arenium intermediate. All right, so the positive charge ends up on the ipso carbon. Right, the other pi bonds are here and here. All right, so you can imagine, because this oxygen has a couple lone electron pairs, non-bonding electrons, right? Those non-bonding electrons can further stabilize that Arenium intermediate through donation into the empty orbital. And what this does is it allows one extra resonance structure for that Arenium intermediate. All right, so this is ortho substitution. Okay, and electron withdrawing groups will stabilize the Arenium intermediate that undergoes, or that was generated from ortho addition. Right? Let's look at para substitution. And for this molecule, we're going to use a different electron donating group. The methyl group, right? And so what's different between methyl and methoxy is that unlike methoxy, which has a lone pair of electrons that can donate into that empty orbital, right? The methyl group does not have those same electrons, okay? And so the mode of stabilization here is a little different than it's going to be here. In this case, the mode of stabilization is going to be hyperconjugation. And this is best illustrated if we take this molecule, which is now flat, and we flip it up like this. So we're looking at it on the side. And so here's our point of addition or point of substitution. Pi bonds are down the side of the benzene ring. It's our hydrogen, one of our hydrogens from the methyl group. And the methyl group, remember, is an sp3 center, so it adopts a tetrahedral geometry. And then here's our p orbital, right? And granted, the p orbital, empty p orbital, is going to be spread around that pi system. Like I said, we're going to use this one resonance structure to best illustrate how the R group stabilizes that electron deficient pi system, right? And so in this case, the carbon-hydrogen sigma bond is going to be able to overlap with the empty orbital on this carbon, okay? And so this is called hyperconjugation. We've seen other examples of hyperconjugation in the first semester of the course and also in this course. Okay, and it's specifically the overlap of the carbon-hydrogen sigma bond overlapping with the empty p orbital on carbon, okay? And so these two modes of stabilization will occur through electron donating groups, right? So if an electron donating group has a pair of electrons, it will stabilize that Arenium intermediate through resonance donation, right? If the electron donating group is an alkyl or a silo group, right, it's really the sigma bonds that overlap with the electron deficient pi system through this hyperconjugation that helps stabilize that Arenium intermediate. Okay, and so what this means, because the ortho and para Arenium intermediates are going to be better stabilized by electron donating groups, right? Electron donating groups are ortho-para directors. Meaning that they're going to direct substitution when it occurs to the ortho and para positions around the ring. Okay? If we look at electron withdrawing groups, okay, now we'll look at something like a nitro group. Again, we're going to investigate the same resonance structure of the Arenium ion that would form from ortho addition. Right? And a nitro group is one of the stronger electron withdrawing groups. Right? And hopefully when we draw the structure, you can very easily see why this would be a high energy intermediate, right? And that's because we have two atoms that are bonded to one another and they both have a positive charge. Right? Which is very, very bad. Okay? If we look at para substitution, what the consequences of para substitution are for an electron poor arene. Right? And in this case, we'll look at a different electron withdrawing group. And a carbonyl. Okay? So here's our arene, right? And you might be looking at this and saying, well, there aren't two positive charges right next to each other, so why would this be so bad? Well, but we have to understand that carbonyl is polarized towards oxygen, right? There's going to be a significant partial negative charge on oxygen, significant partial positive charge on carbon, which is why carbonyls are so electrophilic, so reactive as electrophiles. All right, and as a result, this is also going to be a very high energy intermediate. Okay, so when there's an electron withdrawing group on a benzene ring, when that arene undergoes substitution, it's going to avoid ortho and para substitution because those are going to create very high energy intermediates. All right, so for electron poor arenes, right, electron withdrawing groups are meta directors. Meaning that they will direct substitution primarily to the meta position. Right? In the next video, we're going to take a closer look at the energy diagrams for all of these different pathways and try to compare them from reaction to reaction to reaction.